Today we will continue with chapter 5. We are still in chapter 5, serial communication, where last week we have looked at the overview of the serial communication, and we have gone through the first communication interface or protocol, which is the serial communication interface (SPI) or serial peripheral interface, right? And today we will look at inter-integrated circuit, and we will look at the universal asynchronous receiver transmitter, or in short is UART. So we have looked at the differences between the serial transfer and the parallel transfer, and what are the advantages and disadvantages for both communication method. And we have looked at the asynchronous and synchronous serial communication, where in serial communication we have two methods. Yeah, first one is the asynchronous, and the second one is synchronous. And we have briefly looked at what is asynchronous and synchronous, what are the differences, and we have learned the first protocol, which is the SPI, where we have the which is the synchronous communication. The difference between the synchronous and asynchronous serial communication is that the synchronous serial communication use clock to synchronize the data transfer, whereas the asynchronous communication is not using the clock, where it's used the speed of the data to synchronize the transmission. So we will see today how we do that. And this is example of how we synchronize the data between the transmitter, the sender, and the receiver by using the clock, where each clock cycle will represent one bit, right? So for this, for example, this is the clock cycle, so this will represent bit. This bit is bit 1, right? The value of this one is 1, because in here, if we look at, if we read the data at the positive edge, all right, or positive stroke here, the value of the data is 1. Yeah, for this one the value is 0 for bit 1, and here 0, this one is 1, and so on. So that is how we recognize the data that we receive at the receiver. And this is how we transfer the data, where we have two liners. The first one is the serial data out here, and this one is serial data in for node 1, and this one is the clock, right? So the data for go out and go in is in the different line. For the serial peripheral interface SPI, this is how we connect the peripherals that we want to connect to our microcontroller. We call it slave in this case, and our microcontroller will be the master. And we can see that we connect to all the slave here in using the common bus, the same line, the same bus here, and we have this line to activate, because we use the same bus, means that at one time only one of the slave can access the bus, can use the bus, right? So if you activate more than one, so the data here will be not valid anymore. It will be interfere each other, right? So we have another line to activate the slave whenever we want to communicate with the master, right? So this is how we connect or use the SPI protocol. So we have learned how to use the embed API to use the SPI communication in embed microcontroller, and also we have 4 operation modes for SPI in embed, and this is actually universal. In other microcontroller also use these 4 modes, right? So this is the difference between each mode. This is the way we read the data. For example, if this is the data and we swap the data here, means that the time that we read the data is here. So for mode 0 and mode 1, we can see that when there is no communication between the sender and the receiver, we can see that both clock and data is in at logic 0, right? So we can see logic 0, and the difference between mode 0 and mode 1 is that mode 0 we read the data at the positive clock edge, right? But for mode 1 we read the data at the negative clock edge. That is the difference. And for mode 2 and mode 3, we can see that whenever there is no communication, we can see that the clock line here will be always at logic high, right? Logic 1 here. And mode 2, the data strobe, or we read the data at the negative edge, clock edge here. And for the mode 3, we read the data at the positive clock edge here. So that are the different. So when we use SPI, make sure that if we want to transfer the data, both parties, the sender and the receiver must use the same modes. And this is how we set up the operation at the sender. All right, we need to set the pin for the transmission, and the pin for to select the slave, and this is the format to select the mode. And also the clock frequency need to specify also. So if we want to set our clock frequency at 1 megahertz, so this is how, right? And when we want to send, we just use write. And this one is just the name of our object. When we declare this SPI. So this is object name. So can be any name. So you can rename it using any name that you want. All right, and after that you can use like this, name here, to set the mode, to set the frequency, and to write the data or to send the data. This one is to send the data. And we can see that when we send the data in SPI line like this, when we look at the data, this is the clock, and this is using mode 0, right? So if mode 0, we see that the time that we not communicate, or we not sending the data, we see that the clock is 0, and whenever we want to send the data, we have the clock, and this one is thrown at the positive, right, mode 0. So this means that here positive, we have 0, means that this one is 0, and 1, 0, 0, 0, 0, 0, 1 here. And this is character A, which is actually this is 4 1, yeah, 4 1 as key, right? This is 4E 4 5, this is E, right, in the line, right? This is the same thing. If we want to set our microcontroller to be a slave, this is how. Or if we want to read data, yeah, this one must be the same, right? And to read is dot read, right? So this is the example that we have looked at here last week. So today we will look at the another synchronous communication, serial communication, which is the inter-integrated circuit, or I2C or I2C, right? So this is another communication that was developed by Philips, and today is NXP, the one that manufacture our microcontroller. The LPC 1768 is developed by Philips also. So this communication protocol is developed by Philips, and SPI is developed by Motorola, and this is becoming a standard protocol for serial communication nowadays. Um, so although it is developed by Philips, but other microcontroller, other devices also use this protocol for serial communication, right? Um, why we have I2C, why we have SPI, why we have so many? So because um, each protocol has advantage and disadvantage. Yeah. So when we look at SPI, look at the way we connect between our microcontroller and the peripheral, like this. So we can see that if we have one slave here, all right, so we need how many wires for communication? We have 1, 2, 3. This is a must because this is the line that we use to communicate with the slave, and we have one extra line here to activate this slave. Yeah, so we have, or we need to have 4 wires in order to have this communication. And if we have 2 slaves, so of course this one is fixed 3, but now we have another extra wire here. So instead of 4, we need to add another 1. We have 5 wire now if we have 2 slaves. If we have 3 slaves, we can see that now we have 6 wires, and if we have 4 slaves, now we have 7 wires. So 7 wires. Remember, the advantage of serial communication is that we use fiber line, yeah, fiber liners for communication. But if we have something like this, right? If we have something like this, we use 7 liners already for serial communication. So that is no different with this. So we can see that whenever the number of slave uh, is getting bigger, right? We have more slave to be connected to the microcontroller. We can see that we are going to lose the advantage of serial communication, which is the cost, right? We add the cost of our design. So if we have, for example, more slave, so of course the number of liners is more than parallel communication already. So this is not good, because if we use serial communication, we know already that the data transfer is slow. All right. The good thing about serial communication is the cost. How we can reduce the cost. That is uh, the the point that we choose serial communication rather than parallel communication. But if you have more cost here and the uh, transfer rate is low, then there is no point to use serial communication here. So that is the disadvantage of SPI. Uh, but the advantage of SPI is that if we have uh, less slave, yeah, for example, we have only one-to-one communication or one-to-two, so it is okay, because uh, SPI is actually quite easy to set up, right? The circuit is like this, and also the communication itself is easy. So if we look at uh, the data and the clock here is uh, is straightforward. There is no other information that we need to know, only the clock and the data. All right, and it is fast. Yeah, it is fast. The fastest serial communication protocol, not compared to the parallel, but to other serial communication protocol, because we have no extra bit or extra uh, uh, information. We will see later on, if we use I2C or UART later on, we need extra information here to differentiate the data between the first data and the next data, right? But for SPI, it is only data and the clock. There is no extra bit for to define the data. So it is fast as compared to other serial communication protocol, right? And also it is simple, the simplest one, right? So that is the advantage of SPI communication. But of course, the disadvantage is that if you have more slave, you are going to lose the advantage, the cost advantage of the serial communication. So that's why we have SPI, or Philip developed SPI, the I2C serial communication. So now let's look at the I2C serial communication, how it's work. Uh, this is how we connect the microcontroller to the peripheral or the slave in I2C, where we use only 2 liners for uh, a clock. One is for clock and one is for data. The clock is called as CL, right, or serial clock, and the data is SDA, or serial data. And this is how we have the bus here that connect to the peripheral, and of course all the peripherals share the same bus, just like in SPI. But the different now is that for the data we have only one line instead of 2 in the SPI, right? SPI we have data out and data in, but here we use only one line for data, means that the communication between the microcontroller and the peripheral using one line, means that this one is bidirectional. It can be from the microcontroller to the peripheral or from the peripheral to the microcontroller. And of course, we have the clock. And we need to connect these two liners to the logic high of our supply. So in our case, the microcontroller using a 3.3 volt. So our power supply is 3.3 volt, and we have the pull-up resistor here. Yeah, to pull this line to be always high. All right. So means that if there is no communication, these two liners, clock and data, will be always high, right? So you can see that uh, here, when you add more sleeve or peripheral, all right, you can see that you will not add the wire, or in other words, you not add the cost to your design. See, you just connect like this. No adding wire. So you can have as many peripheral as you want, right? But of course there is a limitation. We will see later what is the limitation, right? But the question is now, because we share the same bus, just like in SPI, we share the same bus here. So in SPI, we activate the peripheral, uh, only one peripheral at one time, right, to access, to use the bus. And this one should be the same, right? We cannot uh, allow more than one peripheral to use the bus at the same time, just like SPI. But now, how to do that here? Because in SPI we have the another line to activate the peripheral whenever we want to communicate or want to use the peripheral. But how we uh, activate the peripheral, only one peripheral at one time, or the correct peripheral at for this I to C. So the idea is to have the address or unique address for each peripheral. Right? For example, this peripheral, the address is address 1. This peripheral, the address is address 2. This peripheral is address 3, and so on. Right? So to use address, and where is that address? How the microcontroller or how the peripheral know uh, what is the address? So that address is need to embed with the data that we send through the line. So whenever the address is correct, for example, we send the address from the microcontroller. For example, we want to connect or want to communicate with peripheral number 3. So this microcontroller need to send the address number 3 to all of the peripheral. Only the peripheral with address 3 will be activated, and the others, because the address is not matched, so the others will not be activated, right? So that is how we activate the the uh, the right peripheral or the right device uh, when we want to use it. So with that, we don't need the extra line for activating the peripheral. Now we need to look at the detail of how the data is transferred, and how the address, or how this one, the microcontroller, is communicate with the peripheral. Because now we don't not like the SPI, where we only send the data between the peripheral and the microcontroller. Now we need to send the address as well, right? So this is how we uh, send the data or communicate between um, the master and the slave, or the microcontroller and the peripheral. This is the data line. This is the clock line. So how to start the communication? So initially both, remember, both are always logic 1, the data and the clock, because we have this connected to the power supply. So it is always 1. So and the master or the microcontroller will control the clock, right? So whenever the master want to write or send the data to the peripheral, or want to read or want to receive the data from the peripheral, so it will pull this line, the data line, to 0. Whenever it pull the data line to 0, means that it want to start the communication, right? And just after that, the clock line will go to 0 and start to run. The clock start to run. And first, the microcontroller will send the address. So the address is 7-bit. There are two protocol actually. You can have a 7-bit address and 10-bit address, but the popular one is the 7-bit. The 10-bit is more complicated. So here we cover the 7-bit address. So the microcontroller will send the address to the through the line, put the address on this line, right? Just like I explained before, that the microcontroller need to send the address first, and the peripheral will respond. So the one with the address that is matched with the address that is sent by the microcontroller will respond. And also the microcontroller or the master will send the signal another bit, which is called the read and write bit. So if this bit number 8, is 1, means that the microcontroller want to read or want to receive the data from the peripheral. But if it is 0, means that the microcontroller want to write or want to send the data. And it will pull the after this bit, either 0 or 1, the line will go back to 1 again, to wait for the sender to acknowledge. So you can see that here the microcontroller and the peripheral need to communicate using this line. This is different from SPI, where there is, although we say that we have communication, but it is actually we only send and receive, right? But this one you need to wait for the sender to acknowledge. This is acknowledge. Acknowledge means that the receiver need to respond to the sender that it is ready for the read or write operation. So this is acknowledge bit, the bit just after this one. And after the acknowledge, so for example, we want to we want to write the data to the peripheral. After the peripheral is give the acknowledge signal to the microcontroller, so the microcontroller will send the data, which is 8-bit, and wait for the acknowledge again. And you can have another data, or you can stop the communication. So to stop the communication, you just stop the clock, means that the clock will go to high and the communication will stop, right? That is briefly explain how this I2C works. So we will see later on in detail, yeah, to understand how it works. Uh, let's look at this. So let's say, for example, we want to create or want to communicate using the I2C communication protocol. So of course, we need to have our microcontroller. So let's, for example, this is our microcontroller. And we have two devices that are connected to the microcontroller. And let's, for example, this is the data line. And of course, we use the same line for the second peripheral. So let's say, for example, this one is peripheral number 1. This is peripheral number 2. This is our microcontroller. And let's, for example, this is the clock line. And we need to connect this to the second one also. And this is data. And this is clock. And of course, this is data. This is clock. And let's say, for example, our peripheral, this address is 1. The address for this one is 2. Yeah, the address is predefined for the peripheral. And now, let's say, for example, we want to do the write operation where we want to transfer the data from the microcontroller to peripheral number 1. Yeah. So how the communication is performed using the I2C communication. So when we look at these two liners, the data and the clock. So for example, this is the data, and this one will be the clock. Here I don't draw the power line, so we assume that we have that one. So I don't want to make thing look complicated, so I don't have I don't draw the power line. Yeah, and remember, for the I2C, you have the power line that connected to both of clock and the data. But in this case, I don't have, I don't draw, because to make it simple. So if we have the power line here, of course, when there is no communication, the signal here will be always 1. Always 1. Yeah, this is logic 1 and this is logic 0. So whenever the microcontroller, which is the master, want to start the communication, in our case, we want to write to the first peripheral, which is P1, right? So what the microcontroller do is that it will pull the data line first to go to 0, means that it want to start the communication, right? Make it 0, and just after that, when this one go to 0, means that the communication is started, and when we start the communication, of course the clock will start to run, right? And when we start here, so the first thing we need to do is to send the address to the SDA line. So the microcontroller will send the address. So the first thing we do is first send address, and this is 7-bit address. So it's 7-bit. So I draw like this, means that this is 7-bit. Okay. So when I draw like this, this means that this one is 7-bit inside here, and the data is, in our case, it should be 0000001, which is 7-bit. So if you look at the signal, it should be 0000001. It should be like this, right? But in this case, I draw in the packet like this. This is 7-bit address, which in our case is this is address, and followed by the next bit, followed by the write or read bit, 1 bit. So if write is logic 0, write is logic 0, and read is logic 1. So in our case, we want to write. So the next bit must be logic 0, and after that the line will go up to 1 automatically, because remember we connect this to power line, and whenever this one go to 1, the peripheral need to respond. So the peripheral that has the correct address, the address that match this, will respond to the microcontroller. So in this case, this one will respond. So how is respond? It's respond by pulling this line down to 0 again. So this is called acknowledge. Acknowledge. So this acknowledge is from peripheral to the microcontroller. All right, it will pull this line down to 0. And when the microcontroller receives this 0, it will know that one of the peripheral has acknowledged or has been activated. Now the microcontroller will send the data. Send the data. So it will send to this line, the same line, and the data is 8-bit, and it will be always 8-bit data, and this is 8-bit, and it will wait for acknowledgement again. All right, it will wait for acknowledge again. So if the receiver here receives the data, it will acknowledge again. So that acknowledge is again logic 0. So the microcontroller will know after it send the data, the 8-bit data, and if the line is 0, means that the data is successfully received by the receiver. And it is up to the microcontroller whether want to send another data or want to terminate the communication. So for example, if it want to send another data, it just send the next data, which is 8-bit again, data, and wait for the acknowledgement. And whenever the receiver receive, it will acknowledge again. Right? Acknowledge again. And for example, we want to terminate the communication here. So what the microcontroller do is the clock is still running. Make the clock 1. Yeah, stop the clock. So means that the communication is terminated. Stop here because the clock is there's no clock already. So the communication is stopped. And if it is stopped, both line will be at logic 1. All right, will be pull up to logic 1. Okay, so that is how the this I2C communication work. Now let's see what if we want to receive the data. If the microcontroller want to receive the data, so the communication protocol, the process is pretty the same, except that the data is now from the peripheral to the microcontroller. So let's see how we do that. So let's see, we want to read from peripheral. Now read from P2. Okay, so let's have that. So again, when we want to read from P2, first, to start the communication, it is the same. The master or the microcontroller will pull the SDA line to 0, and just after that, the clock will start to run. And again, the microcontroller need to send the address first. Yeah, the address is from the microcontroller, and also the clock is from the microcontroller. So send the address. Now the address will be number 2. Once this one get this address, it will respond, right, by send the acknowledge. Right? This one is not respond because the address is not matched, so it will not be activated. And because this one is responding now, it will again send the acknowledge. Send the acknowledge signal to the microcontroller. Now the microcontroller know that, oh, we have this one is respond again. Uh, this one is responding to the communication, and after that it will immediately send the data. Yeah, but this one, the data is from the peripheral to the microcontroller, and it is 8-bit data. And now the microcontroller need to acknowledge, and again the acknowledge is still the same, ACK, but the acknowledge is now from the microcontroller to the peripheral to indicate that the data is successfully received, and here can send another data, or the microcontroller can stop the communication by again make the clock be inactive, or pull it to logic 1, and the communication will stop. Right, so that is how we read. There is no limit of sending data, right, or read data. You can send data as long as the microcontroller not stop the communication. And how many devices that you can connect to the microcontroller? So it is limited by the address. So in our case, we have 7-bit address. So the maximum number of devices or peripheral that can be connected to this microcontroller should be from address 0 to, of course, the last one. But this is ideal case where one address is dedicated to one peripheral. But sometimes the peripheral has the internal register that has the specific address as well. So it's depend. But this is the ideal, and in practice we will not have that many peripheral that are connected to the microcontroller. Then so 7-bit is actually more than enough to have the communication. This is 8 already. It should be 7-bit. Okay, so that is how the communication is done in I2C. Now we will look at how we use I2C in embed microcontroller. So this is the process where we need to specify the object name and the port or the pin that we want to use. So if we look at the embed microcontroller, the I2C, we have two here. The first one is serial data is this P9, clock, serial clock is P10, and the second one is this one, serial data P28 for the data, and for the clock is P27. So in this case, we use this one in this example. So P28, 29. Not P28, 29, actually 28, 27. Yeah, change this. So the SDA is P28, and this one should be 27. Right, in your notes, please uh, make the correction. So based on this, we have 28 for data, 27 for clock, and this is how we set in the embed using the embed I2 API, and the API is I2C. Yeah, this is fixed, and this one is the object name, so you can name anything that you want. So in this example is I2C underscore port, and later on you will use this object for this another setting. So this is how we send the data. This is force start condition, so easy. Yeah, what is force start condition? Force start is that we do this, make the SDA line to 0, start. Yeah, start condition. Right, so easy in embed. Our object name dot start, it will do this. Yeah, start, and of course just after that we need to send the address. So this is how we send the address. Dot write means that we write to the SDA line, and this is the address. The example can be any address. So 52 is just an example, and this is the data that we want to send, 8-bit the data. So same function dot write. Dot write here is dot write also, because we write to the same line, the SDA line. And if we want to write another data, we can have dot write again until we set the stop. So this is the stop condition here, where we stop the clock, make the clock be always 1 here, and it will stop the communication. So this is the stop. And if we set our microcontroller to be a slave, because this peripheral can be anything. The master is the microcontroller, because we can program this, right? But the peripheral can be anything. Can be a sensor, can be a sensor is the input device, where we read from the sensor. But the peripheral can be also the output device, where we can write to it. For example, the LCD, yeah, the LCD, where we send the data to display the data. So the LCD is the output device. The sensor, for example, the temperature sensor, we read the data from the temperature from the sensor. And also the peripheral can be another microcontroller, right? For example, we want to send the data to another microcontroller. So that microcontroller can be uh, defined or as a as a slave. So this is the setting for the microcontroller that we set as a slave. So the API is I2C slave, and the object name can be any name. We name it slave, and to read is very easy. Yeah, we read to the variable. So this is a variable, so can be any name also. So to read is slave dot read, receive the data. So that is how we do. So again, let's look at this example where we have the same configuration as before, where we have these two switches, two LED here. We have another microcontroller as a slave. As a slave, this is the master, and we have the same setting. Here we have the LED, and we have the switches. What we want to do is that now we want to, for example, we want to write the condition of the switch here, and we want to output that condition to the slave, to the another microcontroller. So for example, when we press this switch, and this LED will turn on. Means that the switch condition here is sent to this microcontroller through this SDA line, the data line. And if we press this button, this one will be turned on, for example. So again, we send this condition whether it's off or on through this data line. And this is the example of the program. Look at the program. And again, we have the data that we want to send plus the switch condition. So this is just an example. You can have any, or you can have only 0, right? And the address, let's say the address we set for this slave is 52 or 52 in hexadecimal. And here is the, again, this should be 27, right? I2C, we have I2C port, and this is SDA, this is SCL, data, clock, and we have the LED, P25, P26, P25, sorry, this one, P25, P26, and we have the switches, P5, P6. So LED is, of course, digital out, the switch is digital in, and we have a variable here. The first one is switch word, and we have another variable, receive variable, and we have another variable called ADDR, which is the address 52. So we set predefined here, and we can use in our program. So in the main loop here, so we set this variable switch word to be A0, so can be any actually. The most important thing is that this one. So if IP1 or switch is equal to 1, the switch will be always this value. Yeah, this value be always this value means that we have A1 if switch 1 is pressed. If IP2 is pressed, we have A2, right? Because we all this we have A2. And now let's say, for example, we press the switch number 1 or IP1, so we will send A1 through the SDA. So to start the communication is we use the function start, our object name .start. So we start the process, and we write the address, send the address, and we write the data that we want to send, which is switch word, and in our case it is A1 because this condition is true, and we stop here. So this is sending one byte data, yeah, 1 byte data only, right? And this case is for receiving from the slave, yeah, or we read from the slave. And again, the slave will send the data, the switch condition, its switch condition here, and will turn this LED. Let's see how to read the data from the slave. So this is the read part. So again, the master need to start the communication. So we start, and we write the address, and the address is 52. And remember that 52 is 7-bit, and we need to send whether we need to set whether we want to read or write this. Uh, this one I forgot, right? We need to have the read or write condition. So remember, when we want to send, this one for receive, I forgot the write condition before the acknowledge. The read condition, yeah, the write one is okay, correct? The read condition should be 1. So this is read. So this 7-bit is here, and followed by read before the acknowledge. Okay, so that should be okay. So let's start again. We have, of course, this one will go to 0, and this one just after this, it will start to run until we stop. So here we have the address. We need to send the address, and remember this address is 7-bit. So in our case, the address that we set in the program is 52, and this address combined with another bit, which is read or write in our case, because we want to read from the slave. So it must be logic 1. Yeah, logic 1, and we wait for the acknowledge signal. And this 2 is 7 plus 1 bit, which is 8-bit. 8-bit. So this 52 is actually 7-bit. So 5 is actually 1, 2, 0, 0, 1, 0, 5, 0, 1, 0, 1, and we don't have this 0. Yeah. So this is the address, and we OR with number 1, and we have 1, 0, 1, 0, 0, 1, 1. So this is the read bit. Yeah. So it is embedded in this 8-bit. So if it is a read, so this one should be 0. Right? That is how we do this. So address, we OR this 1 means that we want to read. Then after that we can read. So to read, we read to this variable. So this is our object name dot read. Yeah, and we read from the address. We read from the address, and we stop the condition. Yeah, after we read, we stop, just like this. After we read, we get the data, and we stop. And the acknowledge is sent automatically, yeah, when we receive. and we stop. Stop. And here we want to on this LED. So on this LED, of course, we need to look at what we have received here. Here, what we have received in this variable. So we check. So we can check, right? So this one is to filter out the bit that we don't want. Yeah, we end with number 3, just like what we did last week. So this one, if it is 1, so red LED will be on. If it is 2, the green LED will be on. If both are on, pressed, means that it is 3, so both LED will be turned on here, right? So it depends on what we receive here. To turn on this one means that this condition sent through this and we receive, right? So when you look at the setup, look carefully at this line. So this SDA, you can see that the arrow, you have 2 here, means that this is bidirectional, can be from here to here or from here to here. But for the clock, it is only one way, means that it must be controlled by the master. You can see the clock is from the master to the slave, right? This is another program for the slave for this one, yeah? Because both are microcontrollers, so you need both you need a program, right? And of course this one is not 28 29, but this one 27, yeah, change. So must be 20 27. This one is 20 27. All right, so that will be the I to C. So we are at 9:49. We have another 1 hour, so we will have a short break around 5 minutes and come back at around 5:55 and look at the last protocol, which is the asynchronous serial data communication.